This video will show you how to do more advanced techniques for mass analysis, such as having the software tell you where specific ions has been detected, or if you're looking at a specific ion and determining the elemental composition using a different software package. This already assumes that you know how to navigate through TSS Pro, you know how to calibrate, and you know how to background subtract from spectra. So if you don't, please review the video for that and do a couple of practice runs before you do any of this type of analysis. The first scenario that I want to show you is how to have the software package tell you where a specific ion has been shown. So if you're looking for a specific M over Z that represents the molecule that you synthesized, you can use this technique. In this case, I've analyzed the dollar bill using DART in this region right here, so I'm just going to average an area. And this is already assuming background subtraction. And what I'm looking for is a specific ion, such as M over Z 251.18. So what I can do is hover over this M over Z, have the cursor transform into the arrow, and then left click and drag up into the total ion profile. What this will do is that this will create what's called a reconstructed ion current chromatogram, which means you tell the software to reconstruct an ion profile of solely the highest ion intensities or of the flow of ions of M over Z 251. So in this case, 251 was most abundant in this region right here. So if I average that, you'll see a larger peak of 251, which should be right here. So this will tell you where that ion was shown with the highest abundance. You can do this type of analysis with multiple peaks. So just left click on a specific mass spectral peak and pull that tag up, and you can see all the ions that you're looking at specifically up here. So you can just double click to remove. If you're looking for an M over Z that has not been, or that's not of a high enough intensity to appear on the mass spectrum that you're looking at, what you can do is manually enter this value by clicking this button here. Edit RIC list, so edit the reconstructed ion current chromatogram list. And these were the ones that were dragged up, so they're unchecked right now. And what I'm looking for, because I analyzed the dollar bill, and we all know that the dollar bill has the protonated molecule for cocaine, which is at M over Z 304, I can just type in 304 with an M over Z tolerance of plus or minus 0.5. What I can do is press enter, and this will add this to the list. So what I'm going to be viewing when I click OK is the total ion current chromatogram and the reconstructed ion current chromatogram for M over Z 304. Then I can click OK. This will create the chromatogram, and this region right here will tell me where M over Z 304 was observed at the highest abundance. So then this tells me that 304 was the highest here, so I can just average that and then do the background subtraction. So if I look in the grass, I can see that M over Z 304 is in there at a high enough abundance to select. That's not this, but that's this one right here. So 304, the exact mass for the protonated molecule of cocaine is 304.15488. What was acquired was M over Z 304.1541586. So it's adequate enough to do an elemental composition analysis later on. But the reason why this is slightly in error is because it's not a high enough abundance to get a good centroided mass spectral peak signal. But in this case, it's fine, it's doable, we know that it's there, and we know that it's cocaine. In the case for where I want to confirm that an ion is of a specific elemental composition, or if I want to take it unknown and try to determine its elemental composition, what I can do is average a mass spectrum, or average your mass spectrum. And let's say that I'm looking at this M over Z. Let's see. Let's find a good one. M over Z 309. So what I can do is instead I can save this mass spectrum as a text file by going to this button right here, normally to print, but what I'm going to do is right click on it, go to Preferences, save it as a file. So what this will do is save it as a text file and click OK. And then click on this Send MS to Text File button. And I can just go right click on it, click on Print Mass Spectrum, and this window will pop up to where I can save it. What I do is I just leave it at the default folder and just click Save and save the compressed data that comes with it. Then what I'm going to do is open that saved text file into a different program called Mass Mountaineer, which can be found in the Start menu, shortcut to Mass Mountaineer, which will load soon. So this window will pop up and you have separate tabs, so Spectrum to view the spectrum, Composition, which will be determine a theoretical isotopic peak ratio, and other tools that we won't be using here. The tool that we will be using is this Composition tab right here. So click on that, and what you're going to do is open the MS file, which we just previously saved. And if I click on this button here, the first file is what was saved from TSS Pro. And this is the default that it will grab the most recent file saved from TSS Pro. So I'm just going to click that and then click Open. What you'll get is a mass spectral list of the tabular data and their abundances. And this region right here is the target M over Z that you're clicking on. So if I click on a specific M over Z, it will change right here. There are too many labeled M over Z peaks for me, for my liking, just because the threshold tolerance is too low. So what I'm going to do is change this to 10% to cut down this list. So I change it to 10, press enter, and you can see that any mass spectral peak over the relative ion intensity of 10% has been labeled on this tabulated list. I'm also going to zoom in, so just left click, drag, and that will zoom in. Again, what I was looking at, or what I was interested in through TSS Pro, was this M over Z 309 right here. And it's abundant at about 25%, so it's pretty significant. Pretend that I don't know what this elemental composition is. This was through a reaction mixture, and all I put was carbon-containing compounds, oxygen-containing compounds, and nitrogen-containing compounds. Then I can set these elemental composition limits as such. If I know that there were sulfur atoms in there, then I can put sulfur, so just format it in the same way, 0/10. So that will include 0 to 10 sulfurs. And also, if I knew that there were chlorines or bromines, you can also include that as well. I know for sure that there's no sulfur in these compounds, so I'm just going to omit that. So based off of this accurate mass that was acquired, it's going to work within these elemental limits. I know that the ion is an even electron ion because it has been protonated. And I want to have elemental composition tolerance of 20 millimass units. So what this does is that it will constrain those elemental compositions to to be within a certain error value. Other advanced things that you can do is that if the case that the 309 has a strong X+2 peak, you can click on this button and it will automatically add chlorines, bromines, sulfurs, or silicons into this elemental composition list right here. Alright, so what I can do is that once I set my constraints, I can click calculate, and this spits out a variety of elemental compositions. And based off of, one, the millimass unit errors, so plus or minus 20 will probably not be within your elemental composition range that you've analyzed. It's primarily located within the plus or minus 10 millimass unit range. Also, these elemental compositions are just random, completely random, so it's based off of your intuition to select what is the appropriate assignment. So, in this case, because this was on the dollar bill, this is a ubiquitous compound, and it's not going to be some exotic synthetic compound that you may have created. I can match the isotope peak ratios, so match the theoretical versus the experimental, and you can see that this red theoretical isotopic peak pattern matches very well, except for the X+2. It will match that, and it will also search this elemental composition specifically in the NIST electron ionization fragmentation database. It won't look at the fragments, it will just look up this specific elemental composition. So that will match, give you some kind of match. And what you can do is drag this bar to the right, and you can see that certain elemental compositions have come up with specific hits. So what I'm going to do is look at the elemental composition, which has the lowest error, millimass unit error, and see if that's possible. And you can see that these are the two possible compounds that represent this elemental composition, but that is most likely not it. Remember that this is the dollar bill, and these look like synthetic organic compounds. So what I'm going to do is look down the list of all the possible things. And you can see that this is another possible thing. This is oxybutane, which is a drug derivative, so that could possibly be it. And you can also see all the other compounds with other elemental compositions. And for this specific one, C18H29O4, NIST has 24 hits, which is another possible one, but I highly doubt it because they look like synthetic organic compounds. Again, it's up to you to use your discretion as a chemist to determine what your elemental composition is. Remember, just because it has an NIST search hit doesn't mean that it's your compound. So just remember, use your discretion. So then what I can do is take a look at other things like this not 149, maybe 391 because I know what that is. I'll do an X+2 check. And this also added sulfur and silicon to the elemental limits because of the X+2 values within this mass spectrum. So I believe, so 192, 193, anyways. Those are just possible. You don't have to do the X+2 check. And these, I know for sure that these two elements are not within the elemental composition anyways. But I'm just going to go ahead and proceed and click calculate. So it's going to produce a very, very large list. And then based off of your knowledge as a chemist, you choose an elemental composition that is most suitable for your reaction. In this case, this compound is diethylhexyl phthalate, which is a very common plasticizer.